Okay, so let's pick up where we left off. So we were looking at flipping a coin 5 times. So there was an equal probability of getting a heads or not getting a heads. So we see how the distribution has some real symmetry. Let's consider the following. Let's consider free throws in basketball. And let's just pretend there's someone named David in our class. And David scores 75% or 3/4 of the time he takes a free throw. Okay, so let's look at the possible outcomes and let's consider taking 5 free throws. All right, so if we look at our outcomes, we'll call this baskets, how many he can make. Let's call them free throws, we'll just call them baskets. It is possible that David will make 0 baskets. That would be very sad. He could make 1 out of the 5. He could make 2 out of the 5, 3 out of the 5, 4 out of the 5, or he could make all 5. Now, given that he is 75% likely to make it, we're sort of expecting that he'll make a higher number than 2.5 on average. Okay, so with the coin toss, we saw that it's centered around 2 and 3 when we did it 5 times. So on average, it might come out to be 2.5 times. We're expecting this to shift towards higher basket numbers because instead of having a 50% chance of winning or having a success, there's a 75% chance of success. So let's see how that works in terms of the probability distribution. Probability. All right, so once again, we have the formula that the probability is equal to CNR times P to the R times 1 minus P, that's the chances that we won't get a basket, to the N minus R power. So this was an R as the first exponent, and that's an N minus R as the second exponent. So let's fill this in, all right? So if we look at the first row, this would be the combinations of 5 things taken 0 at a time. There's only one way to do that. We have a 3/4 chance, or 0.75 if you wish, of scoring a basket. So we can take that to the 0th power. If we're going to do this on the calculator, it's probably better to work with the decimals. If we want to, these answers won't be as nice. So it's probably easier to use the decimals. So let's just say 0.75 chance of making it, and he's going to do that 0 times, and he has a 0.25 chance of missing, and he's going to do that all 5 times. Okay, then the second example, that would be, or making 1 basket. There are 5 ways to do that if we look at the combinations, and it's 0.75, he will make 1. So that's to the first power, 0.25, because he's going to not make 4 of them. And then flipping back, this will be the combination of 5, 2. So this is the probability of making 2 of them and not making, let's see, 3 of them. All right, we can keep on going. It's a little time consuming to do this, and you can see why I like to program this into the computer. Because it will do it much faster when these numbers, when we have to do a lot of this. Okay, so this is 5, 4. Okay, and finally, the last one, we're going to use all 5 of them, so there's only one way to do it, and they're all successes and no failures. So when we look at these numbers, I'm not going to compute these all out. I am taking them right off of my MATLAB program that was running the histogram, and the numbers in decimal form are 0, 0, 1, 0. So that's less than 0.1%. Okay, if we make that a percent, chance of not making any. If we look at making 1 basket, So a better percentage. But still, that's only 1.46% chance that he'll only make one. He's more likely to make more baskets. 0.0879. So it's 8.79% chance that he'll make two baskets. So the percentages are growing as the numbers are getting higher. And then we have 0.2637. So there's a pretty high chance that he would make three of the baskets, 26.37% chance. But it's an even higher chance that he would make four of the five baskets, 39.55%. So maybe it'll be even higher than he makes five. And that is wrong. Okay, with a 75% scoring ratio, he actually has a lower chance of scoring five baskets than of scoring four. So we can see this sort of peaks out. We don't know exactly, somewhere in here, around four baskets is the most likely outcome, but it wouldn't be unexpected for him to make three or even to make five. We'd be a little more surprised if he had a bad day and only made two. We'd be shocked if he made one, and we'd be appalled if he didn't make any. Okay. Now, an important thing here, if we look at all of these, they once again add up to one. Now let's graph out this distribution, right? So as before, let's look at where the high number is. It's around 0.4. So let me make each block, let's see, we'll make, that will be 0.1, 0.2, 0.3. Oh, I better go down a little bit more. So we'll go down like this. And here will be 0. This will be a 10% or 0.1, 20%. 30%, we need to get up to about 40% so we can get that highest probability in there. These will be the probabilities. We don't need to go out that far because we only have 5 things. We could make the bins wider, but I'm not going to. So we can look at these probabilities. So we could center them. If I wanted to, I could actually center them in between. So there's 0, 1, 2, 3, 4, and 5. And now I need to get the relative heights about right. Okay, so 0.01, that's a 10th. Oh, actually, that's a 100th of 0.1. So that's barely going to register. I'll just draw almost a flat line down here. We would hardly expect to see that. 0.0146, all right, that's a 10th of this. That's about a 5th of the way. You know, maybe it's right about here. I'm not going to worry too much about getting it exactly right. It just needs to be very low compared to 0.1. 0.0879, that's starting to get up towards 0.1, so that's about here. Okay, and 0.2637, so that one jumps. 0.25 would be here, so right above the 0.25 mark. Put in that block. And then we go up to 0.3955. So we're almost up here at 0.4. All right, and then we drop back down to 0.2375, somewhere around here. Okay, so what we have now is this is skewed to the right. Okay, so we have a set of probabilities that is skewed to the right. It's more likely to be to the right side towards the 5 baskets than it is to be to the left side where the 0 baskets are, because he has a percentage of scoring of 0.75. Now let's look at this in MATLAB and see how, in reality, when you run an experiment a number of times, it doesn't quite work out the way we predict, but as we run it more and more, it will. Okay, here we are back in MATLAB. Let's just run the experiment. And here we've run it once. Okay, so you can see the red boxes, they match pretty nicely with what I've drawn. Mine was a little taller looking and not quite as wide because the scaling is different. But the general shape, we have almost nothing down here at 0 and 1 in red. Then it grows and it peaks around 4 baskets, and it gets lower at 5 baskets. Now, In this particular case, we had David take 5 shots, maybe take a little break, do it again 10 times over. And we're adding up how many times he was able to get each number of baskets. So it looks like he never got 0 baskets out of these 10 tries. He never got 1 basket. A couple of times he may have gotten 2 baskets. He more frequently got 3 baskets in, and he often made 4 of the baskets. But look at this, he never made 5 baskets. So even though it's fairly likely in our little histogram here, in this particular set of experiments of him repeating this 10 times, he never made all 5. Let's see if the next time, wow, look at that. So we have the same probability distribution, but he just had a lot of bad luck. When you do something only 10 times, it's likely that you have a lot of unlucky runs. Okay? So he only was able to make 4 baskets a few times, and he never made 5 baskets, and a lot more times he made 2 baskets or 3 baskets. So that wasn't as good. So let me just keep clicking. Oh, that was a very good set for him. And if we keep going, we can see how erratic this is when we only do it 10 times. All right. Now, this may not be physically possible, but let's pretend that David could do this, shoot 5 baskets, take a quick break, come back and shoot 5 more, and do that 100 times over. It would be a little bit difficult, but let's just pretend he could. Now we can see the data is closer to what we would expect. It still isn't exactly fitting our prediction. So the histogram we come up with is simply just a most likely set of outcomes. It tells us where the probabilities are highest and lowest. When we actually do the experiment, we can, on any given run, it may not fall into the most expected value, which would be 4. Otherwise, it would come up as 4 baskets every single time, since that's the one that was most likely to happen. So over many, many trials, we can see it gets close to, but not exactly matching the distribution curve that we have. Now, if this would be very ridiculous, we would need a robot to do this. If we were doing sets of 50 shots, and the robot had a 75% probability of making it, we could have the robot repeat that experiment 100 times over, and let's see what happens. So now MATLAB can quickly calculate what the distribution should look like in red, and we can see that if we actually then do the experiment 100 times, we have very different outcomes depending on which time we run it. Now, while they're very different, they are all clustering around the middle, the value that we would expect. In this case, it looks like if we took 50 free throws, we would probably make about 38 of them. And so we can see we almost never make below 30. We keep running this. It's rare there's one that has 30 made, but there's one that's just a hair under 30. It looks like maybe we made 29 baskets once, but we never made less than 29 baskets or fewer than 29 baskets. So here you go. You can see it is following the distribution reasonably well, but on any given set of simulations, it's not going to fall exactly onto the predicted values. It will just get close. So all we're doing is predicting what's likely to happen. As we run the simulation more and more times, it gets closer to that. In fact, if we had our robot do this 1,000 times over, assuming the robot doesn't wear out, we can see we're getting much closer to the predictions, right? Now, this is why a casino can afford to do what they do. They know if thousands of people play games of chance, they can predict what will happen over the course of thousands of games on average very well. And they can shade the game so it's slightly in the favor of the casino. And over thousands of games, they make money. The individuals have very erratic experiences where sometimes you lose a lot of money, sometimes you make some money. On average, you lose more than you win, which is why the casino makes money. So hopefully that clarifies things a little bit more, and the way that distributions can lie.